All right, so vocab goes into your spiral notebook. Underneath our vocab, we have two examples of pollutants that usually play a key role in when we're talking about pollution. We're usually talking about these guys. So first is phosphorus. So phosphorus is important. So I've got a smiley face here because it is important for us. It's necessary for ATP, which is cellular energy, and DNA that comes from rocks naturally. So ATP is the cellular energy our cells need just to do their processes. DNA is our genetic information, and so it's all the instructions for what to do with our body inside our cells. And then phosphorus comes from rocks naturally, so it is a natural component of the environment. The problem is, our frowny face over here, is that we put excess phosphorus into the environment through untreated sewage, fertilizer runoff, and detergents. Nitrates are another important component of an ecosystem, and they also have good and bad qualities. So good qualities of nitrates is they are used by the body to dilate our blood vessels, and that helps to lower our blood pressure. So nitrates are used by the body to dilate blood vessels, and that lowers our blood pressure, so that's a good reason why we need nitrates. But again, we put excess into the environment, and that's usually through fertilizer runoff, sewage, and septic systems. So fertilizer runoff, sewage, and septic systems. All right, so the next page covers three vocab terms: biomagnification, thermal pollution, actually four terms: biomagnification, thermal pollution, point source pollution, and non-point source pollution. So we'll start with biomagnification. All right, so I have added dots to this diagram to indicate biomagnification. So this is talking about mercury levels and how they increase with each trophic level. 1 dot equals 1 molecule of mercury. So in water, mercury is kind of dilute, so I only have 1 dot here. But algae use the water in their processes to make plant parts and filters through that water through them. So mercury gets stuck, if you will, in the algae. Because it is fat soluble, these organisms can take mercury in, but then that mercury becomes stored in the cells that have fat in them. So it stores that mercury where the fat's at, because it's fat soluble and you just can't flush that out of your body. Then we have algae eating insects, and so we have more dots of mercury here because at each trophic level, remember our energy pyramid, each trophic level had to consume a whole bunch of organisms in the level below. So algae eating insects have to eat a lot of algae. And so because they eat a lot of algae, they incorporate more mercury into their bodies. And insects that eat these insects, and fish that eat these insects, and fish that eat these fish. And now we have tons of mercury that's being stored in these fish. Then eventually humans eat the fish. And so that mercury doesn't go away. It just gets stored in these organisms. And then humans eat it, and then it's incorporated into our bodies. And unfortunately, mercury is toxic to us, so it can make us sick. All right, next, this picture of a fish kill represents thermal pollution. Rainbow trout are extremely sensitive to changes in temperature. And so if a factory uses water to cool their equipment, and then they dump that warm water back into a pond, that's still pollution, even though there's no harmful chemicals in it. Summer heat decreases the dissolved oxygen in water. That's kind of like if you open up a bottle of soda pop and you leave it on the counter. Eventually it goes flat because all of the carbon dioxide escapes from the liquid that's in there. So if it's hot in the summertime and very stagnant and no wind, no movement of the water, then that water, the oxygen that's in that water, the oxygen leaves that water just like the carbon dioxide leaves the pot. And so essentially the lake water kind of goes flat. If there's no dissolved oxygen in the water, then the bigger organisms don't have anything that they can use to survive. All right, so this map down here shows point source pollution and non-point source pollution. So let's say there's a chlorine contaminant in the lake. We might be tempted to say that it's the swimming pools that are dumping the chlorine in the lake because swimming pools use chlorine. But if you find the chlorine in the lake and you do an investigation and you can trace it back to this discharge pipe that comes from the Copper Kettle Company, we know that there is one source of the pollution, and so that's point source pollution. And that's good because it can help us to have this company, first of all, stop polluting the lake, but also maybe pay for any cleanup that might be involved, or they might have to pay medical bills if somebody gets sick from it. But if it's point source pollution, it's easy to see where it comes from because it's coming from one source. Non-point source pollution is not as easy. So the yellow highlighted represents non-point source pollution. So I might have factory wastes that the steel factory is producing, and then this is a road or a heavily traveled highway, so there might be some rubber or antifreeze or oil or gas that's on the road, so road materials. Maybe there's an illegal trash dump where people are illegally dumping stuff. And then all of a sudden it rains really hard and we have stormwater runoff. So that stormwater runoff is represented by the arrows and it's moving downhill into the lake. Well, now if there's a pollutant in the lake, it's hard to see what was the source of that pollutant because there's not just one place. And so this would represent non-point source pollution because we can't really see easily where the pollutant comes from, especially if it's a pollutant that's in all three places. And so the factory is not going to want to take the responsibility for it if it's coming from the road or coming from the trash dump. And they don't want to pay the money for something that they're not doing, it's coming from somewhere else. So that represents non-point source pollution. All right, on the next page, we have the pH scale and a picture of the pH scale. And that's correct, it should be a lowercase p and a capital H. So the pH scale is a tool that measures how acidic or basic a solution is. And so the pH scale goes from 0 to 7. 7 is considered the neutral value. And as you go to the left, from 7 to the left, as the numbers get smaller, the substance becomes more acidic. As you go from 7 to the right and the numbers get bigger, the substance becomes more basic. Here's a few examples of substances in their pH. Hydrochloric acid is very acidic. It's usually around 0 to 1. pH of 0 to 1. Lemon juice usually has a pH of 2. Coffee has a pH of about 5. Tap water tends to be somewhere between 6 or 7. Hand soap that we use tends to have a pH of 10. Bleach has a pH of around 12 to 13, and drain cleaner can be anywhere from 13 to 14 in their pH. An important process involving pH is neutralization. Neutralization is the reaction of an acid with a base resulting in a neutral solution. And I've put neutral in quotation marks here because we're going to say anything that has a pH from 6 to 8 is going to be considered neutral or neutralized. So neutralization is the reaction of an acid with a base resulting in a neutral solution. So anything between 6 to 8 is going to be considered neutralized. So one example of a neutralization reaction, our stomach acid has a pH of about 2, and let's say we take an antacid that has a pH of 10. So the neutralization reaction will result in a solution that has a pH of 6. So solution of pH of 2, solution pH of 10 ends up with a solution with a pH of 6, and we're going to go ahead and consider that a neutralized solution. So in order to get this value, all you have to do is you add together the values, the pH of each substance. So 2 plus 10 is 12, and then you divide by 2. So 12 divided by 2 gives me the pH of 6. All right, one more example. So out in the environment, oak trees will make the soil acidic. And so maybe it has a pH of 4. Soil might have a pH of 4. Why don't you focus for me? There, that's better. So, soil has a pH of 4, and so you add some lime to the soil. You add fertilizer to the soil, and that lime has a pH of 10. We would have a neutralization reaction. And our ending result would be a pH of 7. So this would be a neutralized substance. So again, we just add together the pH of each substance. So 4 plus 10 is 14. Then we divide by 2. 14 divided by 2 gives me 7.